Hello, my name is Eric. This is a calculus instructional video, and it's the final video in a three-part series. The name of the series is a review of techniques in integration. So it's all about different types of antiderivatives. The previous videos included things like partial fraction decomposition, integration by parts, special powers of trig functions, and even a numeric method like Euler's solution. And there were some slope fields. Well, this video is going to be a little bit more brief, and it's only going to focus on a problem like this. So this is an example of solving the logistic differential equation. Let's take a look. The logistic differential equation typically looks like this. You'll notice that P is supposed to be a population that's growing with respect to time. Time is the independent variable. The differential equation doesn't have a T in it anywhere, does it? So you can tell that in this example, the K value is 0.000025 or 25 millionths. The L that we see here is 4,800. They've done a nice job of writing this equation to look like the model. So what is logistic growth? Well, it's a combination of exponential and bounded growth. In logistic growth, when you graph population as a function of time, the population, if it starts low enough, tends to look exponential. The bigger it gets, the faster it goes. It's got that upwardly concave, exponential, sweeping look. But then something happens. We reach a point of inflection, and the curve transitions to downward concavity because the population begins to feel a constraint coming on. And that constraint is symbolized with an L. I suppose that's for limit. The actual official name of that number, whatever it is called the carrying capacity of the system. And we like to run problems like this in a closed system. So for example, you have a pond with some fish in it. We're not going to add any fish to the pond, and they're not going to jump up and walk away in the middle of the night. It's a closed system, okay? Let's see if we can answer some of these questions now. The first one is, what's the limit as t goes to infinity of p, population? What's the limit as t goes to infinity of the population? Okay, that's a very symbolic way of asking this question. If population is allowed to grow and grow and grow and grow, it will eventually reach an upward bound it cannot get above, and that's that carrying capacity. And in the differential equation, that's found right here. And so essentially, think of it this way, because sometimes they give you this equation in a much less organized way. There are two ways to make this derivative equal to 0, right? If p itself is 0, that factor being 0 would cause the entire product to become 0. So think of that. If p is down here, the rate of growth of population is 0. But it also happens up here at the carrying capacity. When p is 4,800, 4,800 minus 4,800 is 0. So you have 0 times 4,800 times 25 millionths, it's 0. So by the time you reach the carrying capacity, your population's growing at a rate of 0, which means it's not growing. So that was a long-winded answer, but the answer to this is 4,800, and that's 4,800 bass, and that's the carrying capacity of this lake. So again, just look for a way to make this derivative equal to 0. There it is right there, 4,800. And that will give you the upper bound or the carrying capacity of the lake. Next question, how many bass will be in the pond when their numbers are growing most rapidly, and at what rate will the bass population be growing when their population reaches this number? Okay, you can kind of see from the sketch I made that growth is slow in the beginning, Growth is rapid later, and growth slows again near the end of this cycle of reaching the upward bound. Somewhere in the middle here, there's a point of most rapid growth. Well, especially on a multiple choice question, there's a little secret to this, and the secret is that point of inflection or super high growth in population of fish will occur exactly halfway to the carrying capacity. So if the carrying capacity is 4,800, half of 4,800 is 2,400, and that's how many fish you will have when dPdt is a maximum, when the rate of change is positive and greatest. Now, if they ask you to defend this, if you're an instructor, some organization giving you a national calculus test, if they ask you to defend this, you're going to want to say something like this. P prime is a quadratic function of P. With roots of P equals 0 and P equals 2400, or excuse me, P equals 4,800, and a max, you know, where the vertex of the parabola is, at P equals 2,400. I think that would be a sufficient amount of evidence to offer. You might also want to sketch a little graph though. Here's P prime, here's P. Okay, so time has nothing to do with this. If you graph this as a parabola on a calculator or somewhere else, you'll get exactly what we talked about. A root at 0, a root at 4,800, a symmetry axis right between those values, and you'll see an inverted parabola that has a maximum right at P equals 2,400. Okay, so what does that mean? Well, that's where you get your highest value of P prime. That's where your graph of P is increasing most rapidly, right there, point of inflection. Okay? I'm going to scroll this. Oh, no, there's one more thing to answer here. At what rate will the bass population be growing when the number of fish reaches that number? Well, they just want you to plug 2,400 into that. So, dPdt evaluated at P equals 2,400 is 0.00025, 25 millionths, times P, 2,400, times 4,800 minus 2,400. And they're going to let you use a calculator with this, I'm sure. I think what I'm going to do, though, is realize that these are both 2,400, right? So what you have is, what's this? This is 0.00025 times, I'm going to write 24. I know there's supposed to be zeros there, but I took them off. And then here, I go 4,800 minus 2,400 and get 2,400 again. But what about the zeros? Well, how many zeros did I leave out altogether? Yeah, 4 factors of 10 have vanished. I'm going to put those, and I think I dropped a 0 here too, so let's see. I'm going to put the missing zeros here as 10,000. Okay? And then what will happen is 10,000 times this will make 0.25, or 1/4, times 24 times 24. Okay, almost done goofing around. Of course, it would have been faster to grab a calculator. 1/4 of 24 is 6, and 6 times 24, I believe, is 144. So what you get here is 144. What are the units? Well, it's supposed to be a rate of change of fish with respect to time. Time here is given in months. So I guess you get 144 bass per month. Would complete the answer to the many questions that they asked there. I'm going to scroll this, do some erasing, and keep this moving. Okay, part C. Find the values of B, K, L, etc. to write the solution to this differential equation, which is given by this formula. Okay, I want my students to memorize that formula and know how to make all the constants. I think that's a pretty standard expectation. In other words, if you sit down to take a test where the logistic differential equation is going to be featured, you should not expect for them to hand you this. But here it is. So what about the B? What is this B thing? You can solve for this if you forget this formula. I recommend you memorize how to compute B. It's L over the initial population minus 1. So let's see, that's 4,800, I think we had fish. We started with 400. And I'm just going from memory, but that's what's up in the assumptions up there. Minus 1. So that's 12 minus 1 is 11. So I know I'm going to have an 11 right here. And then the other thing I think you should do is compute what K times L is. Because K tends to be small, L tends to be large. And if you're going to write both those numbers up here in this exponent, it's going to make a mess. Okay, so K, geez, what was it? 0.000025. And then L was, I believe it was 4,800. And what does that make? I think it makes 0.12. And let me check that for sure. Indeed, it's 0.12. So, the solution to the differential equation, you know, not just the rate of change, but the thing that will actually allow us to calculate numbers of fish is L over 1 plus 11, that's the B value, times e to the negative K times L was 0.12 T. And I'm going to go ahead and get that going in my calculator because it's going to ask us a bunch of questions here, I can tell. Actually, I think I already have that in there. So let's move on. How many months before the bass population has doubled its initial value? Show your algebra, or if you do this electronically, you at least have to write the equation that you solved. So I don't think I'll go over the electronic solution today. I'll describe it in words quickly. The initial population was 400 bass, excuse me. If you double that, you get 800 bass. So what you could quite literally do is go in your calculator and type y1 equals this. And then you can type y2 equals 800 bass. Graph those two in an appropriate window and use the intersection feature in the calc menu. So a TI-84 in the top row has got 5 buttons. The 4th button is trace, and behind the trace button is a little blue word that says calc. Access using the 2nd button first. So 2nd and then trace, and you'll have a list of things that can be done on the graph. I think number 5 says intersect. And if you were to intersect these two, you would answer the question of when is it that the population of bass gets to, not 80, excuse me, to 800, yes. Well, we're going to do this algebraically, though, because it's more fun. What you do is you put 800 over here, where the population for fish is, and then you just do algebra. Now, there's something that I don't think gets taught often enough. Maybe I'm wrong. Maybe it's the people I work with, you know. But here's a property of fractions everybody should know. If A equals B over C, and assuming things are not zero, it is true that, and conversely, that C equals B over A. In other words, a lot of times when you're solving something, this is especially true in a trigonometry class, and you have a variable down here, you don't have to take 12 different steps to solve. You can quickly trade places with these two, and you'll be well on your way to a very expedient and efficient solution method. So bring this up here, bring the 800 down there. And of course, 4800 divided by 800 is 6, so I have 1 plus 11, e to the negative 0.12, t equals 6. Okay, we're going to do two steps at once now. I'm going to subtract 1 from both sides, and then I'm going to divide by 11. I'm going to do it all at once. Watch me now. 6 minus 1 is 5 divided by 11 is 5 elevenths. I think you know what comes next. Yes, natural log. Take a natural log on both sides. Natural log e to the negative 0.12t is the natural log of 5 elevenths. The point of doing that was to get to this variable, which right now is in the exponential position. So I use the natural logs because of the inverse properties of logs and exponents. I'm very close to the end now, kids. I have negative 0.12t equals natural log 5 elevenths. And go ahead and divide by negative 0.12 and get your calculator ready. Now, if you see this and you start pushing it into your calculator, you may be worried that positive divided by negative, I'm going to get a negative time. No, you're not. You're taking the log of something that's positive but smaller than 1. Folks, these are both negatives. Don't worry, it's going to work out beautifully. So, natural log 5 over 11 divided by negative 0.12. 6.570. That's a t value. So that must be months. Is that a realistic answer? I have no idea. I don't know much about bass and lakes and how quickly fish are able to reproduce. That's a question for somebody else. My name is Eric. Have a great day. And I won't be back for a couple weeks because of severe school closures. Okay. Goodbye.